How many states of matter exist? In school, we're usually taught about 4: liquid, gas, solid, and plasma. However, if you enjoy watching science YouTube channels, you probably know that there are far more states of matter. While researching this topic, I came across videos listing 15, 17, and even 22 states of matter. These often include exotic phases like excitonium, time crystals, quantum dots, and more. Instead of chasing sheer numbers, I suggest focusing on understanding the logic behind how matter transforms under changing conditions and why these changes fundamentally alter its properties and behavior. Even if we ignore exotic states, there are already more than 3 states of matter. For instance, by increasing both temperature and pressure on a liquid, you can create a supercritical fluid. In this state, matter has a density close to that of a liquid, but exhibits extremely low viscosity and no surface tension. This makes supercritical fluids useful as solvents. For example, carbon dioxide becomes supercritical at 31 degrees Celsius and 73 atmospheres, making it an effective solvent for organic compounds. This property, for example, is used in chromatography to separate complex mixtures. Water, however, requires much more extreme conditions to reach its supercritical state: 374 degrees Celsius and 215 atmospheres, conditions that exist on Venus, where water in the lower atmosphere is likely supercritical. Some also consider amorphous solids as a separate state of matter. These substances resemble solids in density, but lack a crystalline structure, behaving more like very viscous liquids. Most substances can transition to an amorphous state under rapid cooling. For example, ordinary ice can become amorphous if cooled quickly. However, amorphous states are often unstable and tend to crystallize over time. With some flexibility, liquid crystals might also be considered a separate state of matter. In liquid crystals, molecules share a common orientation, like in regular crystals, but can move freely like in liquids. These materials, which we discussed in a previous video, are common in practical applications like LCDs. However, liquid crystals typically occur in highly asymmetrical organic molecules, making it debatable whether they count as a separate state. So, even within the familiar temperature and pressure ranges studied in school, there are more than 3 states of matter. The variety of conditions in the universe is far greater. Next, let's explore the state of matter typically referred to as the 4th, plasma. As you likely know, plasma is an ionized gas, meaning a gas composed not of electrically neutral molecules, but of charged ions and electrons. For instance, a regular gas transitions into this state at sufficiently high temperatures when the kinetic energy of molecular motion becomes large enough to cause significant damage upon collisions. Molecules break apart, and their constituent atoms lose electrons, leading to ionization. It is important to note that plasma is not always fully ionized. In most cases, it still contains a substantial number of neutral molecules or atoms. This is because ionization, the process of knocking electrons off atoms or molecules, occurs alongside recombination, where electrons reattach to ions to form neutral particles. During recombination, energy equal to that required to detach the electron is released, often in the form of electromagnetic radiation, including visible light. This is partly why plasma typically glows. On the other hand, a certain amount of ionized particles is always present in any gas, even in ordinary air. The distinction between plasma and a partially ionized gas is therefore somewhat blurred. Physicists have established specific criteria to define plasma. For example, in plasma, the energy of electrical interactions between particles, essentially the potential energy described by Coulomb's law, must be at least comparable to or greater than their kinetic energy. From this, an interesting conclusion follows. Although plasma is generally associated with high temperatures, it is not always extremely hot. Like other states of matter, the transition to plasma depends not only on temperature, but also on pressure. For instance, plasma can form at relatively low temperatures under very low pressures, such as in a gas discharge lamp, which contains plasma even at room temperature due to the influence of an external electric field. Similarly, cosmic gas exists in a plasma state even at temperatures close to absolute zero. For example, the Boomerang Nebula, PGC 307-4547, contains plasma with a temperature of about 1 Kelvin, just 1 degree above absolute zero. Yet it is still considered true plasma. Metals, surprisingly, also fit the definition of plasma in terms of particle density within a Debye sphere. Their crystalline lattices consist of ions surrounded by a gas of quasi-free electrons, making the density of charged particles in metals quite high. In a sense, metals can be considered solid plasma. Conversely, fire, often cited as an example of plasma, typically does not meet the scientific definition of plasma, despite its high temperature and the presence of charged particles. Nonetheless, in most cases, plasma is indeed hot, typically heated to thousands or tens of thousands of degrees. At such high temperatures, matter exists solely in the plasma state. While plasma is classified as a distinct state of matter, thermodynamically, it closely resembles a gas. However, it can be a very unusual gas. For instance, the plasma in the Sun's core has a density of 150 grams per cubic centimeter, 150 times the density of water and much greater than even the densest metals on Earth. This occurs due to the immense pressure created by the weight of the Sun's outer layers. Despite this high density, the material in the solar core remains roughly gas-like from a thermodynamic perspective, because the kinetic energy of its particles at temperatures of around 15 million degrees far exceeds the potential energy of their mutual attraction. Since plasma consists of charged particles, its properties differ significantly from those of ordinary gases. Electromagnetic forces between the particles are significant even at distances where typical interatomic and intermolecular forces can be neglected. Moreover, unlike most gases, which generally consist of a single type of particle, e.g., oxygen gas comprises oxygen molecules, plasma is essentially a mixture of two gases with distinct properties: a gas of light, negatively charged electrons, and a gas of heavy, positively charged ions. The temperatures and other characteristics of these two components within the same plasma sample can vary greatly. For instance, in so-called cold plasma, ions and neutral atoms or molecules may have temperatures close to or below room temperature, while the electrons can have kinetic energies corresponding to thousands or tens of thousands of degrees. It should also be noted that any flow of matter in plasma essentially constitutes an electric current, which generates a magnetic field that affects neighboring particles. This dynamic causes plasma to behave quite differently from ordinary gases. For example, plasma tends to form into specific threads or filaments, a phenomenon known as filamentation. This process explains the characteristic fibrous appearance of cosmic nebulae, which are vast clouds of cosmic plasma. The study of plasma physics is a vast and critical field of science, with magnetohydrodynamics as a key area. While we have touched on magnetohydrodynamics in some of our previous discussions and will likely revisit it in the future, today's focus shifts to exploring the states of matter under even more extreme conditions of heating and compression. Imagine plasma at very high temperatures, hundreds of thousands or millions of degrees. At this point, molecules have long disintegrated into constituent atoms, and these atoms are fully ionized, stripped of all electrons. The resulting state of matter resembles a soup of atomic nuclei, composed of protons and neutrons, suspended in a sea of free electrons. The kinetic energy of this soup is immense, and such plasma can only remain stable under significant external pressure that prevents expansion and cooling. If we compress this plasma further, its density and temperature rise, and the distance between particles decreases. Eventually, quantum mechanics comes into play, transitioning the matter into a fundamentally new state. This transformation involves the concept of wave-particle duality, which posits that quantum particles, e.g. electrons, protons, and neutrons, exhibit wave-like properties. Each particle lacks a precise position in space and instead exists as a probability wave, known as the de Broglie wave, which represents the likelihood of finding the particle in a particular location. Additionally, the Pauli exclusion principle states that no two fermions, particles like electrons, protons, and neutrons with half-integer spin, can occupy the same quantum state within the same spatial volume. This principle limits the spatial compression of such particles, leading to the formation of a new state of matter, degenerate gas. When the distance between particles becomes smaller than the wavelength of their de Broglie waves, further compression becomes impossible, and the plasma transitions into a nearly incompressible state resembling a liquid. This degenerate matter state is defined by the average interparticle distance equaling the de Broglie wavelength under the given conditions. The de Broglie wavelength is inversely proportional to a particle's momentum, which can be expressed in terms of kinetic energy at non-relativistic speeds. For a given temperature, lighter particles, like electrons, will have longer de Broglie wavelengths than heavier ones, like atomic nuclei. Thus, in compressing plasma, degeneracy first occurs in the electron gas component, forming a degenerate electron gas. This phenomenon is more common in astrophysical contexts, such as the cores of massive stars or compact objects like white dwarfs. At typical plasma temperatures of tens of thousands of degrees, degeneracy occurs at pressures of millions of atmospheres. Scientists believe that degenerate electron gas exists in the cores of massive planets like Jupiter and in the centers of stars. In white dwarfs, remnants of stars that have exhausted their nuclear fuel, the matter consists entirely of degenerate electron gas, resulting in extreme densities, millions of grams per cubic centimeter, and high surface temperatures, hundreds of thousands of degrees. Paradoxically, the hotter a white dwarf is, the more it contracts, as the degenerate electron gas compresses under higher temperatures. This relationship leads to an inverse correlation between mass and size. The more massive a white dwarf, the smaller it is. Once matter reaches the state of degenerate electron gas, it cannot be further compressed, regardless of pressure. However, its state can still change with temperature. As temperature rises, this dense matter undergoes another remarkable transformation at certain stages. At certain temperatures and densities, the process known as electron capture becomes highly probable. In this phenomenon, plasma electrons collide with atomic nuclei and are absorbed by protons, converting them into neutrons. This process is called neutronization and has two significant consequences. Firstly, the concentration of electrons drops sharply, lifting the degeneracy and making the plasma compressible again. Simultaneously, it ceases to be plasma in the traditional sense, as both the absorbed electrons and the protons, transformed into neutrons, largely vanish. What remains is a form of matter consisting almost entirely of neutral neutrons, known as neutronium. While neutronium often features in science fiction with fantastical properties like incredible strength, used, for example, in crafting spaceship armor, real neutronium is unsuitable for such purposes. First, neutronium likely behaves more like a supercritical fluid rather than a solid, making it impossible to fashion into solid structures. Neutronium's density is staggering, about 10 to the power of 15 grams per cubic centimeter. A single teaspoon of neutronium would weigh as much as Mount Everest, rendering any large-scale use impractical. Most critically, neutronium can exist stably only under extreme pressures and temperatures. A free neutron is unstable, undergoing beta decay, transforming into a proton and emitting an electron, with a half-life of around 15 minutes. For neutronium to remain intact, the beta decay must be balanced by electron capture, which requires temperatures in the hundreds of millions of degrees and pressures around 10 to the power of 20 atmospheres. In normal conditions, neutronium would rapidly disintegrate or even explode, like a powerful nuclear bomb due to the energy released during beta decay. Such conditions are found only in a few places in the universe, such as the interiors of neutron stars, and even there, only at specific depths. The theoretical understanding of neutron matter is still developing. Unlike ordinary matter or plasma, where interactions are dominated by electromagnetic forces, the interactions in neutron matter are governed by the strong nuclear force, which is far more complex and challenging to model accurately. If neutron matter is further compressed, it reaches another degeneracy state, this time of neutron matter itself occurring at even higher pressures. As the temperature increases and the matter is compressed further, a new phase transition occurs, altering the structure of the matter. At temperatures around 1 billion degrees, collisions between neutrons become so energetic that they break down the neutrons themselves, releasing their constituent quarks and gluons. This transition forms a state of matter called quark-gluon plasma, analogous to ordinary plasma, but consisting of the building blocks of neutrons and protons, quarks, and the gluons binding them. Quark-gluon plasma requires extreme conditions to form. temperatures in the billions of degrees and matching pressures. However, it has been artificially created in high-energy particle accelerators. In these experiments, charged particles are accelerated to kinetic energies corresponding to temperatures of trillions of degrees, and their collisions produce tiny, short-lived quantities of quark-gluon plasma. This plasma quickly undergoes a process called hadronization, in which the quarks recombine into composite particles. Stable quark-gluon plasma might only exist in areas of the universe where temperatures and pressures remain consistently extreme, possibly in the cores of neutron stars, though this is uncertain. Further heating of quark-gluon plasma leads to the formation of an even more enigmatic state of matter, first observed at the Large Hadron Collider in 2012, glasma. In glasma, individual quarks and gluons cannot be distinguished, existing instead as complex excitations of a field called the hadron field. Currently, very little is known about glasma due to its incredibly brief lifespan. While quark-gluon plasma survives for about 10 to the power 0 of minus 9 seconds before hadronizing, glasma exists for just 10 to the power of minus 24 seconds, 10 trillion times less than quark-gluon plasma, before transitioning back into quark-gluon plasma. Now, shifting to the opposite end of the temperature spectrum, consider what happens when substances are cooled to temperatures near absolute zero. Extreme cooling also induces phase transitions that result in new states of matter, distinct from the high-temperature phenomena described above. Interestingly, these low-temperature states echo some characteristics of degenerate gases, where the de Broglie wavelength of particles becomes comparable to their interparticle distances. However, the focus here shifts from fermions, particles like electrons, protons, and neutrons with half-integer spin, to bosons, particles with integer spin described by Bose-Einstein statistics. In principle, when cooled, bosons behave similarly to fermions in the sense that their de Broglie wavelength increases. However, the Pauli exclusion principle does not apply to bosons. Not only can they occupy the same quantum state, but they also tend to do so, particularly under conditions of extreme cooling, where they accumulate in the state of minimum energy and momentum, essentially zero kinetic energy and momentum. It's worth noting that in quantum physics, the phrase state of zero energy and momentum does not mean that the particle's kinetic energy and momentum are exactly zero. If that were the case, it would lead to a paradoxical situation. According to the Heisenberg uncertainty principle, the more precisely a particle's momentum is known, the less precisely its position can be determined, and vice versa. If the momentum of particles were exactly zero, known with absolute precision, their position would become entirely indeterminate, effectively spreading them across the entire universe. For an observer on Earth, such a particle would essentially disappear. This does not happen, so even in a state close to absolute zero, particles, in this case atoms, retain some minimal energy and momentum, the lowest values allowed, which cannot be further reduced. When most or all particles of a substance reach this state of minimal energy and momentum under extreme cooling, the substance forms what is known as a quantum condensate. Since the substance in question consists of bosons, this specific state is called a Bose-Einstein condensate, BEC. The de Broglie wavelength of particles in a BEC, due to the extremely low temperatures, becomes comparable to the dimensions of the entire object made up of these particles. This means it becomes impossible to define where one particle ends and another begins. Essentially, the entire object behaves as a single quantum mechanical entity with all the associated peculiarities of quantum mechanics. This property fascinates physicists as it allows for the creation of macroscopic objects governed by quantum laws. Such properties are crucial for technologies like qubits in quantum computers. Additionally, BECs enable quantum simulations, scaled-up models of certain quantum systems. These simulations provide insights into processes such as electrical conductivity and the transition to superconductivity. In a BEC, particles do not exchange energy or momentum since all particles share the same energy and momentum, which are at their minimum possible values. This leads to phenomena like superfluidity, where substances in this state lose viscosity, surface tension, and other properties resulting from interparticle interactions. BECs exhibit numerous anomalous and seemingly paradoxical properties, many of which remain only partially explained. As such, their study is a cutting-edge field in modern science. Achieving and analyzing these states requires the ability to cool substances to ultra-low temperatures, a topic discussed in one of our previous videos. To summarize our journey through the states of matter, beyond the schoolbook states of gas, liquid, and solid, we've mentioned supercritical fluids, amorphous solids, and liquid crystals. With further cooling, we encounter quantum condensates with their remarkable properties. Heating and increasing pressure lead to states such as plasma, degenerate electron gas, neutron matter, quark-gluon plasma, and finally glasma. Altogether, this gives us a neat total of 12 states of matter. Of course, this is not the limit. If desired, one could count dispersive systems, exotic states like excitonium, Rydberg matter, strange matter, time crystals, quantum dots, spin glasses, and so on as separate states. We will explore some of these fascinating forms in future videos. For now, thank you, take care, and see you next time on our channel.